What if space itself can crack? And what if some of those cracks are still stretching across the cosmos today? Cracks in the fabric of the universe. When we picture the universe, we tend to imagine it as smooth and continuous, and in this seamless fabric of space and time stretching out in every direction. Galaxies drift, stars burn, gravity bends space-time, but the stage itself feels intact. No seams, no joints, no cracks. But the early universe was not calm, settled, or tidy. It was hot beyond comprehension, dense beyond intuition, and changing faster than almost any physical process we know today. And when things cool quickly, they don't always cool perfectly. Sometimes they crack. Cosmic strings, if they exist, would be literal cracks in the fabric of the universe, not tears you could poke a finger through, but ultra-thin defects in space-time itself, relics of the universe's earliest moments, frozen in place as reality cooled and crystallized, not objects floating in space, but flaws of space, scars left over from the birth of the cosmos. That phrase, cosmic string, unfortunately causes no end of confusion, so let's clear something up immediately. Despite the name, cosmic strings are not the same as the strings of string theory. They do not vibrate to create particles, they do not require extra dimensions, and they do not live at the Planck scale, though they were born there if they do indeed exist at all. The overlap in names is historical and deeply misleading. Cosmic strings are a cosmology problem, not a particle physics one. To understand what they really are, we need to talk about topological defects, a term that sounds intimidating but describes something very familiar. It's winter here in Ohio at the moment, so let me use an example that comes to mind. Imagine a pond freezing over. As ice forms, different patches crystallize independently, each choosing a slightly different orientation. Where those patches meet, the fit is not perfect, yet cracks and seams. The ice did not crack later. The cracks formed because of how freezing works when it happens quickly over a large area. The same thing happens in cooling metal, drying mud, or poured concrete. The faster and larger the phase change, the harder it is to keep everything aligned everywhere at once. The flaws are not accidents, they are inevitable. Topology, sometimes nicknamed rubber sheet geometry, looks at how shapes behave when they're stretched or bent without being torn or cut, and helps explain why some mismatches simply can't be smoothed away. Take a flat, two-dimensional map and try wrapping it smoothly around a sphere, or since I'm writing this right after Christmas, wrapping a round object nice and neat. You can't do it without folds, creases, or distortions somewhere. Those unavoidable mismatches are not defects in the material so much as consequences of geometry itself. And they make a useful everyday analogy for why topological defects can form in the universe without anything actually breaking. In topology, you're free to bend and stretch shapes continuously, but you can't tear them or glue new pieces on, and a topological defect is something that cannot be removed by any amount of such smooth deformation. A topological defect isn't a weak spot you can smooth away locally. It is baked into the overall geometry of how something settled into its final state. Like a knot in a rope, you can stretch it or move it around, but you cannot remove it without cutting the rope itself. The early universe went through a series of dramatic phase transitions like this, if cosmic inflation theory is right, of course. We had a brief moment where the whole universe, very tiny and ultra-hot, suddenly expanded so fast that no forces, all of which move at light speed or slower, could cover the distance between particles. So for a moment the universe was unglued and also suddenly vastly expanded, and it cooled to trillions of its prior temperature, which still might have been a trillion Kelvin after that, or just a hair over absolute zero. Lots of uncertainty here. When inflation ended, that temperature would rapidly rebound to somewhere between a billion and a quadrillion Kelvin, which is still trillions of times cooler than pre-inflation, but far hotter than the inside of any star. This is the moment, and it was much, much shorter than a second, when the universe basically hiccuped and began falling into its present form. What happened right before, during, and right after, all compressed into a time shorter than a nanosecond, and it determined the fate of the universe. Forces were once unified and split apart, symmetries broke, fields settled into lower energy configurations, and because all this happened everywhere, nearly simultaneously, without distant regions being able to coordinate their choices, mismatches were unavoidable. Those mismatches are what we call topological defects. Depending on how a symmetry breaks, you can get different kinds of defects. As we discussed in our Big Bang trilogy over the summer, symmetry breaking can sound arcane, but the idea itself is simple. Imagine two balls. One sits at the bottom of a dip, Push it even harder and it will roll around but eventually settle back at the bottom unless you give enough energy to push it over the rim into a different valley. The bottom position is stable. Now imagine a second ball balanced perfectly on top of a hill. As long as everything is flawless, it stays there, but the slightest nudge sends it rolling down one side. Once it does, the symmetry is gone. The hill now has more ball on one side than the other. The balanced state was metastable, and breaking it selects a direction that did not exist before. A quick aside. In the quantum world, you don't always need to push the ball over the rim. Quantum tunneling is the phenomena where a system doesn't quite have enough energy to cross the barrier and still has a small chance of ending up on the other side anyway. The closer it gets to the top, the better those odds become. It's a minor tangent here, but it comes up a lot when we talk about early universe physics and end-of-time physics too. That's essentially what symmetry breaking means in the early universe. As inflation ended and fields relaxed into lower energy states, tiny, unavoidable variations determined how forces and properties emerged. Had inflation unfolded slightly differently, those outcomes might have differed too, leaving behind different remnants and defects. From defects to cosmic strings. Some defects form at points, some along lines, and some across entire surfaces. Magnetic monopoles would be point-like defects. Domain walls would be sheet-like, and if those existed in abundance, the universe would look radically different and likely be very hostile to life. Magnetic monopoles will be getting their own episode, along with the discussion of super-strong mag matter, a hypothetical material made from them instead of atoms, so make sure to hit the like, subscribe, and notification buttons so that you do not miss that episode. Anyway, cosmic strings fall neatly in between. They are line-like defects, potentially stretching thousands or even millions of light years, yet so incredibly thin that even the most powerful microscopes imaginable wouldn't resolve their width. In some models, a cosmic string could be thinner than a proton while carrying the mass of a mountain in every centimeter of its length. That sounds paradoxical, but it highlights a crucial point. Cosmic strings are not made of matter in the usual sense. They are regions where space-time itself failed to settle in the same configuration as its surroundings. Their energy is not stored in particles, but in the structure of the field, tension locked in the geometry of reality. And tension is exactly the right word. If cosmic strings exist, they are under immense tension, pulling straight with a force that dwarfs anything we can engineer. That tension keeps them thin, stable, and extraordinarily energetic. Cut a cosmic string, if that were even possible, and the ends would not unravel. They'd snap back at near light speed. They have that much tension in them. What makes cosmic strings especially fascinating is they don't behave like ordinary massive objects. They don't pull things toward them the way stars or black holes do. Instead, they change the shape of the space around them. Also, unlike black holes, cosmic strings do not slowly disappear through quantum evaporation or Hawking radiation. They lose energy the old-fashioned way, by shaking space-time itself and radiating gravitational waves. That also means we can't use them to power things the way we potentially could with a Kugelblitz black hole. Space near a cosmic string would be subtly incomplete, as though a narrow wedge had been removed and the remaining edges stitched together. Locally, space is flat. Globally, it is not. Light passing by does not curve inward, it travels straight, but ends up in places it should not. Which means if a cosmic string passed between us and a distant galaxy, we would not see a smeared arc or an Einstein ring. We see two identical images of the same galaxy, side by side, perfectly sharp and undistorted. No magnification, no warped shapes, just duplication. That signature is so distinctive that it's one of the primary ways astronomers search for cosmic strings today. If we ever found two galaxies that were demonstrably the same object, same spectrum, same redshift, same structure, with no visible lensing mass in between, it would be extraordinarily difficult to explain it any other way. But geometry is only half the story, the other half is motion. Cosmic strings would not sit still. In most models, they move at a significant fraction of the speed of light, oscillating under their own tension. When strings intersect, they can reconnect, pinching off closed loops. Those loops would oscillate and gradually lose energy, primarily by radiating gravitational waves. That makes cosmic string loops a potential source of gravitational radiation, not rare catastrophic bursts like black hole mergers, but a persistent background hum, punctuated by sharp, directional flashes when loops form cusps or kinks. Modern gravitational wave observatories are only now reaching the sensitivities needed to probe these possibilities, too, so we haven't seen them yet, but wouldn't expect to. Cosmic strings also wouldn't be gentle neighbors. If a fast-moving string swept through matter, the damage wouldn't come from gravitational tides, but from geometry snapping past at relativistic speed. In extreme cases, the effect would resemble an infinitely sharp blade moving at near light speed, though the odds of such an encounter are thankfully vanishingly small. Crucially, cosmic strings would not decay quickly. As topological defects, they don't simply evaporate like particles. They lose energy slowly, again mainly through gravitational radiation, and large strings could persist for the entire age of the universe. If they formed early and were not diluted away, they could still be threatening the cosmos today. All of this leads to a strange conclusion. Cosmic strings will be simultaneously fragile and indestructible, breakable into loops, stretchable across cosmic distances, yet impossible to erase. Their existence will be written directly into the geometry of space-time. Which brings us to an obvious question. If cosmic strings are so well motivated, why haven't we seen one? The short answer is inflation. Cosmic strings would have formed extremely early, during symmetry-breaking events at energy scales far beyond anything we can reproduce. If nothing dramatic happened afterward, we might expect the universe to be laced with them today. But inflation, a brief period of runaway expansion we discussed earlier, would have stretched space so violently that anything embedded within it was diluted. If cosmic strings formed before inflation, they were not destroyed, they were simply pushed far beyond our observable horizon. Or most of them anyway. That neatly explains their absence, but it could also leave a loophole. Cosmic strings could still exist if they formed after inflation ended, during later phase transitions. Those strings would be weaker and rarer and therefore harder to detect. So far, every research agrees on one thing. If cosmic strings exist, they must be rare, weak, or both. I tend to be rather skeptical of them myself, but we'll note that this is not a failure of the theory, it's information. Every upper limit on cosmic string tension rules out entire classes of early universe models. It tells us which symmetry-breaking events did not happen, or did not happen late enough, or did not have the properties some theories predicted. In that sense, cosmic strings are valuable, whether we find them or not. They are also optional. The universe works just fine without them. Inflation, dark matter, and large-scale structure do not require cosmic strings to exist. That's what makes them scientifically clean. We are not trying to rescue a theory by invoking them. We're testing whether the universe left behind scars we can still see. If cosmic strings were discovered tomorrow, it would be revolutionary. Not because it fixes a problem, because they would confirm that space-time itself once underwent violent phase changes, leaving permanent defects behind. And if they are never found, that too tells us something profound about the universe cooling, settling, and avoiding certain kinds of imperfections. In cosmology, absence is often as meaningful as presence, which makes sense. Cosmology is about space, and the thing about space is there's an awful lot of space, and it's almost entirely empty. So cosmic strings occupy a rare place in physics. They are dramatic enough to reshape our understanding of the early universe, but restrained enough that their non-existence doesn't collapse anything we rely on. Optional fossils, relics that might still be quietly threading space-time, or might lie forever beyond our horizon. Next, we'll set aside likelihood and turn to imagination. Carefully constrained imagination, though. If cosmic strings do exist, what could an advanced civilization do with them? Could they be used, tamed, exploited, or they remain cosmic hazards, powerful but untouchable? Well, that's where the speculation begins. Civilizations and cosmic strings, tools, traps, and temptations. Once you admit the possibility that cosmic strings exist, it becomes almost impossible not to ask the next question: what would you do with one? Because a cosmic string is, in a sense, pre-built infrastructure, not the kind you'd ever choose if you had other options. But if you are an advanced civilization that can detect them, track them, and survive near them, a cosmic string isn't just a relic of an early universe. It's a resource, a hazard, a highway, a weapon, a piece of cosmic terrain, all at once. The first and most obvious use is as a gravitational and geometric oddity you can exploit for navigation, observation, and communication. If a cosmic string produces distinctive double imaging of distant objects, it becomes a natural beacon, a permanent signpost you can triangulate against at interstellar or even intergalactic ranges. You might not be able to see the string directly, but you can see the fingerprints it leaves on the light behind it. A civilization with long baseline telescopes could map a string's position and momentum, then treat it like a moving coordinate axis etched into the sky. It would also become a kind of cosmic telescope mount, not a lens that magnifies, but a lens that duplicates. If you can place sensors in the right geometry relative to a string and a target, you could gather the same object's light along multiple paths, compare them, and extract subtle information. That might sound like a minor gain, but for a civilization doing serious astronomy across hundreds of millions of light years, a few extra handles on geometry can be priceless. More exotic uses come from motion and tension. As noted, a long cosmic string is under immense tension, and it wants to be straight. Loops oscillate. Long strings whip and vibrate, and when they intersect, they can reconnect and shed loops. That means a cosmic string network is constantly trying to simplify itself, shedding energy as gravitational waves. If you could control that process, even a little, you'd have a bizarre kind of power station. Not a generator that burns fuel, but one that encourages a cosmic object to radiate gravitational waves in a preferred direction at a preferred cadence. The engineering would be obscene, even by SFIA standards. The efficiency might be terrible. The payoff might still be worth it, because you're not mining a planet or lifting a mountain. You're encouraging the universe to ring like a bell and catching the vibration. Then there's the more grounded, if still mind-bending possibility, using strings as momentum exchangers. A cosmic string doesn't behave like ordinary mass, but still has inertia, and more importantly exists as a stable line embedded in spacetime. If you can attach it, or more plausibly, interact with it through fields or carefully arranged masses without physically touching it, you could transfer momentum between your spacecraft and the string. Now, that sounds like cheating, but it's not reactionist proportion in the magical sense. You're pushing on the universe's defect and letting it push back. You're using a pre-existing cosmic object as your reaction mass. Probably even better than black holes for using as interstellar hubs and highways, and channel regulars know how valuable black holes are as real estate, in spite of what sci-fi tends to imply. So if cosmic strings exist and could actually be used that way, there would be a natural temptation for a civilization willing to gamble entire star systems for a shortcut. And hey, what's a star system here and there when you have billions of them? But it is a gamble because every practical use comes with a matching catastrophe. A fast-moving string is a relativistic knife. You don't need to hit your planet, you just need to pass through your neighborhood. Even if the probability is tiny, a civilization playing for millions of years doesn't get to ignore tiny probabilities. If cosmic strings exist, any sufficiently long-lived civilization would likely build a whole branch of string weather forecasting, tracking candidate signatures and projecting their motion, the way we track asteroids and comets. Except this comet is not a dirty snowball, it's a defect in spacetime with the potential to cut a planet in half. And that cuts both ways. You cannot talk about cosmic strings and not acknowledge weaponization. If you could steer a string segment, or even steer the intersection of strings so the loop production happened where you wanted, you'd have a weapon that makes antimatter look polite. A string doesn't have to explode, it just has to pass through. A close flyby might scramble orbits, a direct transit could carve a world in half. A controlled loop oscillating nearby could produce gravitational wave effects that are hard to shield against and would be even harder to explain to someone who didn't see it coming. And remember, this is a gravitational effect, so it's not just slicing in half like a sharp wire. A star or planet cut in half that way would be effectively unaffected, same as you can't cut an ocean in half with a knife. This knife cuts differently. Of course, this knife analogy requires an assumption of control, and control is the biggest question of all. Cosmic strings are not manufactured artifacts, they are leftovers from physics at scales we barely comprehend. The string's material is not atoms you can weld, it's the configuration of a field. Anchoring one, reshaping one, cutting one, those might be impossible even for civilizations that can build Dyson swarms, because the string is not a structure you assembled, it's a feature of the universe you're trying to bully into doing what you want. Absent being able to set off controlled big bangs that don't wreck the universe around you, there's no obvious way to make these things. Which means the most realistic civilizational relationship with a cosmic string might not be exploitation at all. It might be avoidance. If cosmic strings exist, they're less like a resource deposit and more like a fault line. You do not mine the San Andreas Fault. You build your bridges away from it and keep very nervous eyes on the seismographs nearby. And if you're clever, you might harness it indirectly, not by grabbing it, but by planning around it, using it as a boundary marker, a navigational reference, or a dangerous region you exploit the way sailors exploit trade winds without controlling the atmosphere itself. If cosmic strings exist, they are literal cracks in reality, and cracks are where you learn how something is made. Which brings us to our last section, the close cousins people confuse them with, why cosmic strings are only loosely related to string theory despite the name, and what it would mean for physics if we ever confirmed even one. Today we're talking about cosmic strings, possible cracks in space-time itself, stretching across the universe. If you enjoy exploring ideas at that kind of scale, That's exactly the territory I cover in Settling Saturn's Rings, this month's exclusive. We look at how one of the solar system's most iconic features could become a massive construction zone, supporting habitats, industry, and infrastructure on a scale that starts to rival planetary systems. For several years now, I've been releasing monthly exclusives and bonus content on Nebula, where every episode of SFA appears early and completely ad-free. That includes over 800 episodes, along with content from hundreds of the creators like Everyday Astronaut, a space and science show that breaks down rockets, spacecraft, and real-world missions in a way that makes even the most complex systems feel approachable. Go watch Settling Saturn's Rings and use my link or the QR code to get 50% off an annual plan. Just $30 for the whole year. Cousins, confusion, and what a discovery would mean. Cosmic strings sit in a strange niche. They are famous, dramatic, and weirdly easy to visualize, and yet they are also easy to misunderstand because they share a name with something else entirely, akin to dark matter and dark energy, which are only tangentially related. So let's separate the family tree here. When cosmologists talk about cosmic strings, they mean line-like topological defects, leftovers from the early universe phase transitions we discussed. When particle physicists talk about strings in string theory, they mean fundamental vibrating objects whose modes correspond to particles, usually requiring extra dimensions in a very different mathematical framework. The similarity is mostly linguistic. By and large, they have nothing more in common with each other than a violin, which also has strings. The universe does not owe us tidy naming conventions, and physicists tend to be bad about making them anyway. That said, there is a bridge between the ideas that's real enough to mention: cosmic superstrings. In some versions of string theory, it's possible for extended string-like objects to stretch to astronomical scales and behave in ways that resemble cosmic strings. If those exist, they might be detected by similar signatures, lensing or gravitational waves, but their detailed behavior could differ. In practice, from the point of view of an astronomer trying to find a long, thin thing that warps spacetime in a distinctive way, that distinction may only matter after discovery, not before. And cosmic strings are only one member of a broader category of possible early universe scars. There are other topological defects: magnetic monopoles, textures, and domain walls. Monopoles are point-like and again with their own episode soon. Textures are more diffuse and tend to unwind rather than persist as stable structures. Domain walls are sheet-like, and they are a nightmare scenario. If they were common, they'd dominate the universe's energy budget and carve space into incompatible regions. The fact that our universe looks as smooth and habitable as it does tells us domain walls, at least in the abundant form, probably do not exist in this universe. And of course, if the observable universe is just a tiny portion of the wider cosmos, which we think is indeed the case, we might have just lucked out, and none exist in our Hubble volume. One more worrisome weight on the anthropic principle and fine-tuned universe conundrums. Cosmic strings are in that sense the nice defect, the ones that can exist without breaking everything, which is why they're such a useful scientific target. Nothing fundamentally alters the universe we find or exclude them. For now, the real value of cosmic strings is not that they would be cool cosmic hazards or potential megastructure materials, like magmatter made out of magnetic monopoles. It's they would be evidence that spacetime carries fossils. They would mean the universe remembers. We live in a cosmos where stars are born, burn, and die, where galaxies collide, where black holes merge, where even spacetime can ripple. We often think of the universe as something that evolves but forgets, eras replaced by new eras, old physics hidden behind new conditions. Cosmic strings are the opposite of that. They're the possibility that the earliest moments left behind a permanent mark, a seam that never fully healed. In some scenarios, akin to those in conformal cyclic cosmology, they might leave fingerprints of older universes behind. Cosmic strings do not cross universes, but their echoes might, and maybe that's the real reason they capture our imagination. If a cosmic string exists somewhere out there in the dark between galaxies, it's not just a curiosity. It's a message from the universe's infancy, a note written in geometry instead of ink, still legible after billions of years. A crack in the fabric of the universe, and a reminder that even reality itself may have grown up fast, cooled too quickly, and kept a few scars to prove it.